And you've already heard from him a few times already in this monthly session and even in prior monthly events. His name is Javier Fernandez-Marques, and he is freshly joined Flower Labs. So welcome, Javier, as a member of Flower Labs, but also, perhaps more importantly, welcome to Flower Monthly to tell everyone about how they can squeeze out their last little bit of performance when they want to run a simulation because, I don't know, a neuropsychological deadline is looming, or they just need to understand how this method is going to work in production, perhaps when they scale it out. So yeah, thanks for joining us today and telling us about simulation.
Yes, of course. Happy to tell you about it. Okay, can I share? I'll share my screen. Can you see it?
Yep, looks great to me.
Okay, okay, then let's start. So in this talk, I'm aiming for roughly 20 minutes. And what I want to tell you about are some a common set of tricks or ways of working with Flower that I usually use in my projects, at least for the last 2.5 years or so that I've been using Flower for either demos or papers. So let's start in directly. All the code I'm going to be showing some snippets of code, and I won't be going into them in all detail. I will only highlight some lines of code, but all the code is now in this repo that you can clone and play with it, either during the talk or after the talk. And also, just to make some publicity, we're increasing our activity in Twitter, so feel free to follow us. And if you have any questions, technical questions, or you just want to join the Flower community, feel free to join our Slack channel. So I'll start by giving 3 examples of how you can configure your strategies in Flower. But before jumping into it, I'm going to explain very briefly what a strategy is. So you can think of a strategy as the director of an orchestra, where the orchestra is the federated learning experiment you want to run. And in that way, the strategy orchestrates different stages like sampling clients, deciding how we aggregate the updates that the clients send back to the server, and other aspects like, for example, how we are going to evaluate the global model after the aggregation. So one cool thing you can do with Flower very easily is to change how we sample clients. By default, the clients are sampled by uniformly sampling all the clients that are currently connected to the server. But in some situations, you might want to change this. For example, here, what I'm changing is in the first round, I do random sampling, but then in subsequent rounds, what I do is I have defined a variable that I call tip ratio that will set some clients to be resampled in the following round. And here I'm doing exactly that. I'm maintaining some of the clients, and then the remaining clients are sampled as usual using the client manager. You can override configure fit method in your strategy to do other type of sampling. For example, you can sample clients based on their CO2 emissions at a particular point in time. This was presented in the Flower Summit last week. Or you want to also override this method to send specific instructions to different clients. For example, you might have highly capable clients, so you want to send them a big model to train. More constrained clients, you might want to send them a smaller model to train, or a smaller version of the bigger model. So these are some examples of things you can do when you customize the configured method in your Flower strategies. Another method you can change in your strategy is what is called aggregate fit, which defines how the updated models on the clients are aggregated to generate a new global model. For example, in this strategy, I'm inheriting from Fed average. But let's say I want to implement a method that stochastically drops a certain percentage of the updates. One reason why you would want to do this is, for example, to simulate scenarios where clients fail. So these updates are never sent back to the server, or you want to simulate a communication channel failure. You can even do more sophisticated things. For example, you can, once you get the model updates from the clients, you can assign different weighting to each of them based on, for example, auxiliary data set you have in your server. You can do that here. Or you want to implement a brand new aggregation methodology based on potentially previous states of the global model. These are some things you can do when you change the aggregate fit method in your strategies. And usually at the end of every round in Flower, we need to evaluate the new global model that has just been created from the aggregation stage. By default, this happens after every single round, but in some settings, you might want not to do it after every single round, because, for example, maybe the convergence rate of your experiment is not so fast, so you would only observe changes every, let's say, every 5 rounds or every training rounds, or even every more rounds. So in this snippet of code, I'm changing exactly that functionality. I'm saying, okay, I want to run the evaluation of my global model according to the variable I have defined called eval every n, which I have set up to be by default 5. So these are 3 methods. Normally, you want to consider modifying your Flower strategies to better help you with your experiments. Now I'm gonna still talk about the strategies and a bit about the clients, but in 2 particular use cases that some people are really starting to look into with a lot of detail. And one of them is to send multiple models to the clients instead of a single model, which is the typical setup in federated learning. And also I will be showing you how you can retrieve metrics from the clients very easily, because normally clients, we only care about the model updated on the clients and how it is used on the server, but we can send additional statistics that might be helpful in simulations. So let's say we want to send multiple models. One scenario where we would want to do that is if we want to do some form of knowledge distillation on the client side. So for that, the model we train in federation would be the student, but we still need to give the clients, we need to give them a teacher, and a pre-trained teacher, to be exact. So how can we send this model to the clients? Well, the easiest way would be to incorporate this teacher model into the instructions we send to the clients. So one obvious way of doing it will be to override the configure fit method in your strategies. That, as we saw earlier, is also in charge of sampling clients. But here, we don't touch that part, and instead we add additional components to the config dictionary. In this case, the teacher model, as well as some parameters for performing the knowledge distillation stage. Then the clients that have been sampled in this particular round will receive, as usual, the model that is being trained, that is being federated, in this case, a student, as well as a dictionary that here it is called config, that contains the teacher that we can use, and we can instantiate it and then pass it to our new training function that will be doing some knowledge distillation. So this is an example on how to send multiple models to your clients. For distillation, makes sense to work like this. In other settings, for example, you might want to do multimodal training, where you have one model that looks maybe to the images in a video, and another different model that looks into the audio of the video. So you would use a similar formulation to make sure that these 2 models can be trained by your clients. And then last but not least, usually the way the fit method returns has the following signature. So we send the model, the parameters that have been updated by the clients. Typically, we send how many training examples were in the local data set. This is a statistic typically used by Fed average, but it's not compulsory. And there is another third element that is by default an empty Python dictionary, where you can add anything you want. Ideally, you would be adding small bits of information. Like, for example, I want to time how long it took to do local training. Another thing you could send, for example, based on the previous talk, you could send the statistics of the sparsity ratio of the masks that the clients use within every batch, for example. So that information can be sent in this Python dictionary. And then how do you get that information back in the server? So you would need to look into the aggregate feed method in the strategy, because it's the one that receives the updates from the clients. And then you can retrieve this dictionary, Python dictionary, which is called metrics in the Flower API. You can retrieve it like this. So this is one very convenient way of using the metrics in Flower. And now the last block or the last part of my talk is going to be about how to run Flower simulations effectively. And the idea of Flower simulations with FL simulation with Flower is that you can run exactly the same code, whether you are developing on your laptop or you are running it on a GPU server you might have on your lab, or even if you have access to a multi-node setup in your data center, you can still reuse exactly the same code. So I think probably I don't need to motivate a lot why we want to do simulation in FL. But if I have to highlight two main reasons is, one, normally we cannot have access to a large number of clients. For example, maybe we can, if we are very lucky, we can have access to 10, let's say, smartphones or 10 Raspberry Pis, maybe 100 if we are super lucky, but it's not realistic to have access to several thousands. Not to mention the cost of managing them. So we can simulate very easily clients as simple standalone Python processes. So this is what simulation allows us to do. And this is what the virtual client proxy in Flower exactly does. The virtual client proxy makes use of another toolkit to launch virtual clients in a resource-aware manner, which also allows you to very flexibly scale to much larger systems to run your federated learning workloads. And this dynamically scaling of your workloads is exactly the point I'm going to be talking about in the following 2 or 3 slides. So let's say that you have written let's say you already have all your Flower code that you run on a few devices, maybe through the standard gRPC API. And now you decide to work in a simulation setting. You don't need to change anything in the code except how you start the experiment. So instead of having a start server, you will have this line, start simulation, which requires one additional argument called client resources, which is a standard Python dictionary where you need to specify what are the number of CPU threads you would like to allocate to every client participating in the round, and what is the ratio of GPU resources that this client needs. So for example, if you have a laptop with 10 CPU threads and you want to run 10 clients in the round, if you set that every client needs 1 CPU thread, you can run all the 10 clients concurrently at the same time within the round. But for example, if your clients are too computationally expensive because maybe the model is a bit larger, you would be better off allocating maybe 5 CPU threads to every client. So this means that you can still run a round with 10 clients per round, but instead of all being running at the same time, they will be running 2 at a time, right? 5 CPU threads will be spent by one client, another 5 will be used by another. Once one of these clients finishes, another client will be spawned and do their local training. And this will happen until the round is completed. Let's say that you now have access to a system that you have GPU resources. So a similar logic can be applied to this setup. You can have a large, let's say a memory-intensive training pipeline. For example, here I'm federating a vision transformer for ImageNet with a reasonable batch size, 64. And because this has a fairly large memory footprint, I have decided I can only afford having 2 clients in my GPU. Here, what I'm stating is that every client should be allocated half of the GPU memory resources. If on the contrary, let's say my federated learning research let's say my new strategy I'm developing allows for clients to train with a much smaller batch size. For example, here I have reduced it to 8. Then you can afford reducing the resources needed for every client. And as it is the case here, I'm able to pack 8 VAT clients at a time in the same GPU. This, of course, comes with different implications. Some of them are positive. Usually, the more clients I can pack concurrently, the faster my simulation runs. But you need to bear in mind that that can likely lead to more memory usage. For example, here you can see that my memory utilization is close to 22 gigabytes of system memory, and here is double. So these are some factors to take into account. But let's say that you're super lucky and you have access to multiple machines, not a single machine with GPUs. So how do I interconnect all these machines together with Flower? And the way to do this is by using simulation in a slightly different way. Normally, when you launch a virtual client engine, a server for the Ray toolkit is being created behind the scenes. But when you want to interconnect multiple nodes, it's better to do this process in a different way. So for example, what you need to do is to change your code. So you specify the initialization argument for Ray to set the address to auto. And what this means is that when you launch the code, it will look for an already running Ray server in your system. How do you launch the Ray server? You just go to your terminal and you can do Ray start -- head. That will create the head node of your system. Then you open another terminal, let's say on your second machine or all your machines you have. And then you just need to copy the line of code shown in the message where on the terminal you initialize the head from. Copy it, and that will ensure that that second node is attached to your head. So which means that the virtual client engine will be able to see the complete pool of CPU and GPU resources available. And then you can go back to your main node and launch the experiment as usual without any change in the code. Of course, the moment you start running parallel jobs, the moment you start adding new machines, the moment you want to run things at the highest possible efficiency, you need to take into account certain considerations. One of the main aspects is to understand, okay, what is the memory footprint and compute footprint that my clients require? How much VRAM my model needs? Once you have understood that, you can set what are the CPU and GPU resources that every client will need. What if I want to run things even faster? Well, maybe you need to understand first where the bottlenecks are. Are the bottlenecks the lack of concurrent clients running on the same GPU? Or is the bottleneck the way I'm accessing the data set in my file system? And finally, as I mentioned, when you work with simulation, you are working effectively with two different tools. We have the open source framework Flower as well as Ray, and they have been evolving in slightly different ways. So it is so in my advice is that for the best experience is not to use the absolute latest version of Ray, but instead use an earlier version that is not so old anyway, which is the one I highlight here with this command. In simulation, sometimes maybe your experiments will fail because your client is reading data from not the right directory, for example. So before launching the experiment again, you want to ensure that there are no hanging processes in your system. So you can stop everything running this command Ray stop -f. And also if you encounter any issue or if you have a new cool feature about how you use simulation in your experiments, feel free to reach out to me on Slack. If you have an issue, reach out to me anyway or anyone in the team, or open a GitHub issue with the simulation label. This is everything I wanted to share. Once again, you can find the code for all the experiments and all the ideas I've been highlighting in this talk. And I'm very happy to take questions if there are any.
Thank you. Another great presentation. I've got to say this has been a sort of a hot button issue for people on our Slack lately. And so it's great that you took some time out to describe, albeit at a high level, some of the approaches to getting the most out of the simulation engine. Let me see what questions I can see. Okay, one person is asking, they're basically saying they have this Ray version thing that you mentioned, fine. But if they, what do you do as an experienced user when you run out of memory? So they're running the simulation, it's not an issue to do with this Ray thing, but then the thing blows up. It's like they're getting out of memory errors. What can they do? I guess they're kind of getting at what can they do to debug the issue? Where do they start?
Yeah. Yes, it's a good question. So what I generally do is basically my first point here. Sometimes like you start a new experiment and you have a rough sense of, oh, this is a big model or this is a small model, but big or a small model, basically the moment you want to parallelize things on GPU, even a few megabytes make a big difference. So my advice and what I generally do is let me run simulation with one client per round. And with that, it allows me to see, oh, with one client per round, this is how much memory a single client needs. And it has access to the entire GPU. So based on that, okay, I can see that I'm using 2 gigabytes. I have 8 gigabytes on my GPU. Well, technically, I should be able to pack 4 in concurrently, but that might be pushing it too close to the limit. So maybe realistically, I can only pack 3 or 2 because the global model also needs to run somewhere. So that is my advice. The first advice. The second advice is make sure that your clients are not maybe recording any unnecessary data on the GPU. Maybe you are keeping track of the activations and you forgot to send them from GPU down to CPU. This is a very typical issue that might arise if you are starting to debug something and then you forgot to remove that line of code, for example.
Sure, that makes sense. I guess as a follow-up question, there was one just saying, what is your favorite method for profiling memory usage?
My favorite method to profile memory usage is for sure NVIDIA SMI. If I need to go into much finer resolution than what you can see in NVIDIA SMI, I've been using the PyTorch profiler a lot, but I do that generally outside of federated learning. Like you can use a PyTorch profiler in isolation with the model you are trying to federate, and maybe you can see, and you will be seeing at very fine resolutions what is the memory peak of every stage of your model. I see.
So you're doing that in a centralized setting to get a good feel for the memory sort of bottlenecks and where they are and so on, and that informs when you kind of go back into the federated world.
Yeah. Yes. You don't need to design a complete centralized federated centralized setting. You just need to get your model and maybe even just passing some batches of data through your model. That's enough to capture the memory signature of your model.
I see.
That's what I would do.
I see. Cool. Let's see if anything else. I guess we'll make this the final question. And they're saying, what's the I guess what is the largest simulation that you've run personally? Like I guess maybe number of clients and the amount of data set, or what's the largest?
The largest, probably 4 GPU machines, so 32 GPUs, and likely concurrently maybe 8 clients per round. No, 8 clients in every GPU, so 8 by 32 clients concurrently running. Probably the largest I've recently run for sure.
Oh, so it's like 4 racks of 8. So,
no, for both. Yes, 4 racks of 8. Yes, 4 machines with 8 GPUs each of them.
Yeah, 4 machines with 8 GPUs each, 32 GPUs.
Yeah, and like big GPUs, and then you can very easily pack even fairly big models. You can pack several within every GPU.
Oh, I see. Okay, I guess that must answer their question. I guess they're curious what you've been up to. Yeah, well then we're sort of running out of time for Flower Monthly now. So if you stop sharing, I will share our
sharing.
I will share our. Oops. Let's see if I can do this. And does everyone see the screen?
Yes.
Great. Well then, this is the end of Flower Monthly. I just want to say thank you everyone for coming to Flower Monthly June. Our next Flower Monthly will be July 5th. That's the first Wednesday of July. It'll be 4 p.m. UTC, so the same start time that we had this week. I want to say thank you very much to Berivan and Javier for two wonderful kind of like completely separate, on the different spectrum talks. One, deeply researchy, really interesting stuff. How do we build on a lot of ticket hypothesis, and how do we build the next generation of FL methods? And then we had Javier talking about what are the nuts and bolts. How are we going to do that practically speaking? How do we scale these things up? How do we just get to A to B right now when we want to do a simulation? So two really useful talks here. So thank you both so much for being with us this month. And I'll just conclude by saying, let's see, we have the Flower Monthly Slack channel. If you're interested, you can catch up with all of the different videos of Flower Monthly. So this event will get posted in the coming weeks or so. We've got a bit of a backlog from Flower Summit naturally. And so the video of this event will be posted. You can find it on our YouTube channel. You can also find it on this website that you see listed on this slide. Join the Slack if you haven't done so already. And then one new addition that we haven't really advertised too much yet is that we have a calendar of events. So it's a Google Calendar, I believe, where you have all the various Flower events are populated there. So if you're kind of curious, you want to get a reminder for when Flower Monthly is, it's a great way to see Flower Monthly in your own time zone and not get confused. You can subscribe by following this URL, this nice friendly URL of flower.dev/Flower events calendar. So that's all the announcements. Thank you everyone for joining us, and I will catch you all next month. Take care.
Thank you.
Thank you.
Yeah.
Thank you.
Bye-bye.
Bye-bye.
Bye.